Thank you. So this is Bill Langdon. What I'm actually going to do is cheat. So for those in the room, the presentation is allegedly on the gem5 glib Heap Fitness Landscape. What I'm actually going to do is talk about that and then talk about some follow-up work. So where we took the results from gem5 and it applied to 4 other large C++ programs. And essentially what I'm going to be talking about is this colored picture. So we're going to talk about fitness landscapes. And this one is nice because A, it's an easy problem, and B, we can put it on a slide. So most fitness landscapes are horrendously large and horrendously complicated. Here we have a simple one we can put together in 2 dimensions. No? Bear with me. We have technical support coming. To page down.
So, what's it going
on? How did you do that?
I don't know. I just clicked this.
Yay! Thank you. So to give away the result from the GI paper, which should be in the proceedings, the workshop, we got a 12% saving. And so encouraged by that, I wanted to look at other programs. And again, to give away the answer, we get a nice smooth fitness landscape, but we don't get such a large improvement. So the talk is going to be a bit about gem5, the GNU Heap Fitness Landscape. As I said, why I think this is a nice landscape, a little bit about the tools we're using for measuring the heap in terms of how many bytes are actually being used by these various programs. I was going to talk a little bit about Magpie, but since we've had an excellent tutorial, I will keep that quite short. And then the last part of the talk is going to be looking at 4 other large C++ programs, where, as I've said, we get some improvement, but really it's not as impressive as we got for gem5. So gem5 itself is more than 1 million lines of C++. What it does is simulate the operation of very large silicon chips, principally CPUs. I'm going to be talking about the Intel 8086 instruction set, but gem5 is used for a lot of different problems, mostly CPU and memory architectures, but it's also been used for FPGAs. There will be a talk on Friday where we use gem5 as a benchmark for some LLM work demonstrating testing of large programs. And the basic idea with gem5 is it simulates the operation of CPUs. So it simulates in some considerable detail. So if you want to work out how fast your ARM computer is going to be before you actually build it, it does that sort of level of simulation. The basic time unit of resolution is 1/10 of a nanosecond. So whenever something interesting happens within the CPU, events are created within the gem5 simulation software. Those end up being on the heap. They remain on the heap while the event is in progress. When the event has been processed, they remove from the heap. So during the operation of gem5, things are being continuously added and removed from the gem5 heap. So it's a very dynamic operation. And in a typical run, literally millions of events will be simulated. Events will be added and removed from the heap. In terms of C++, in the GNU world, it boils down to using exactly the same routines as C code. So where you would be doing something like a delete or creating a new object in C++, those will be translated into malloc and free recalls. And from our point of view,
Hit this part.
okay. So from our point of view, although the GNU C runtime library has got 37 different tunable parameters, 7 of those relate to the heap. We're going to concentrate on 3 of those, which are shown in bold. And what I want to say is, although that's only 3 parameters, they boil down to quite a large search space, more than 10 to the 48. Thank you. But as computer scientists, we should not be scared of numbers like 10 to the 48, despite the fact that it is larger than the number of particles in the observable universe. By computing standards, this is a small number, and it certainly translates into an easy search problem. So what I'm going to assume is people have probably come across search landscapes. A fitness landscape is essentially the idea of having a search where we add an extra dimension. So in the graph at the bottom of the page, we add the Z dimension, the vertical dimension, to represent the fitness. So here is a very simple 2D problem. Each of the points in the 2D service has 4 neighbors, which are represented by the lines. And the vertical axis represents how good that is. So in this problem, better is higher. And so we can see that in the center, that's where the optimal fitness is. But in this contrived example, the optimal fitness is surrounded by a moat of low fitness values. And it's most of the time, these diagrams are pictorial. In this work, we're going to be able to show you a genuine 2D fitness landscape where the Z dimension corresponds to reductions in the size of the heap. So for a program that's written in C++ using the GNU compiler, there are only 3 parameters which are actually relevant, assuming, as in the gem5 case, we're dealing with a single-threaded program. One of those, this mmmax, doesn't really make a lot of difference. So from experimenting, it really doesn't make any difference. So we can reduce our 3-dimensional search to 2 dimensions, as we have on the left-hand side. The orange color represents almost no fitness change. The nice thing from our point of view is the bright yellow corresponds to approximately a 10% saving in heap. What I should stress is there is an awful lot of bright yellow. As a fraction of the landscape, it's not huge, but it's not difficult to find. On the right-hand side, I've added arrows. Since this is a triple log plot, it's difficult to see the gradient. And what the arrows do is emphasize that although the fitness landscape is smooth, it's not flat. And so around the good part of the search space, there's a large base of an attraction where search should be guided towards the better parts of the search landscape. And then you can see there are various parts where you can set parameters and makes things very much worse than the default behavior. But they're finding the bright yellow should be easy for most search techniques. In terms of the gem5, what we're going to do is use the malloc info function. So this is a function provided by the GNU-C runtime library. It's nice that it gives you a precise snapshot of the heap at the current point with almost no overhead. In the second part, we're going to use Valgrind's tool Massive, which is nice in the sense it gives you the peak heap usage over the whole run, but it does have quite a large overhead. And gem5 itself is something with a large overhead. Bobby was saying that for a typical gem5 run, it's about 100,000 times slower than real time. So we're going to add some more runtime overhead on the top of that using Massive. So that's a downside for Massive. And other ones, top, you're probably already familiar with, just a Unix utility. And during Amric's talk, he mentioned perf, which will again can be used to measure memory consumption. In terms of, again, Magpie, Amric's already mentioned a lot of this. So typically Magpie is used for tuning source code. What we showed back in EuroGP 2018 was search can be used to tune large numbers of parameters. What we're going to do here is use Magpie and another tool called CMAES for tuning parameters. What we use in Magpie is we use its geometric distribution of mutations. So this is essentially like an integer version of an exponential distribution. We set the defaults for the mutation to be the same as the defaults that the GNU library itself uses. One thing I should have mentioned earlier is we don't actually need to change anything inside the program. The GNU-C library can be programmed through the use of environmental variables. So by setting up environmental variables of the right name, we can change the way the heap behaves without code changes. And for the point of view of fitness, the fitness is going to be the difference between the peak heap usage with a change to the parameters, and that will guide Magpie. And for both Magpie and CMAS, we're going to use 1,000 trials. So I've been told to speed up, so I'm going to skip that one. And also that one. Essentially for CMAS, we have the same setup as Magpie. It's a continuous optimizer. So we simply map doubles into integers. And we get similar sort of results that Magpie and CMS both find this an easy problem to solve. So that was the first part. The second part, we were going to look at 4 other large C++ programs. Z3, which is Microsoft's theorem prover. We actually use a benchmark suggested by Centaura prover, who are a rival to Magpie. I put in this benchmark into the SMT competition last year, so fairly up-to-date problem. Two compilers, the GNU C++ compiler itself, and the Clang LLVM compiler, both running on the largest source code out of MySQL, something like 15,000 lines of code. With the include files, it bulks up to 200,000 lines of code. And the last one is the Regis key value store, which is about 15,000 lines of C++. And we use the benchmark provided by Regis. And the upshot of that is essentially, again, we see a smooth landscape. So each of the colored lines here represents a 1D slice out of the whole search landscape. The arrows, which hopefully are visible, show that although a lot of the graph shows a smooth, flat area, it's not actually flat. There is a gradient. So there is something that Magpie and CMAS should be able to find. But the upshot on that was we didn't get much of an improvement. So something like a 1.5% improvement. And the other programs are similarly disappointing. Smooth landscape, but not much of an overall improvement. So what I was going to talk about was briefly why I think those programs are not giving us the sort of improvements we're seeing with gem5. I suspect 3 of the cases are simply because the programs are radically different. What they do is they read a file. Maybe it's a source file. Maybe it's a description of the theorem we want Z3 to prove. They read that. As they read it and process it, they increase the size of the heap, but they don't dynamically add to the heap and remove as the way gem5 does. And so my supposition is we're not seeing much of an improvement because there's less work coming to the heap. All it needs to do is add stuff. It doesn't really have to remember how to delete it at all. And with the Regis benchmark, I suspect the reason we're not seeing much is all the elements added to the heap are the same size. So it doesn't have to keep track of the holes in the heap. Every time it adds something, it's exactly the same size. So there shouldn't be a problem with fragmentation. How long? I'm going to interpret that as you can speak for as long as you like. So these 5 graphs are from top. So going across the bottom, we got time at different scales. So I haven't actually put the units in because the whole thing is dominated by how long it actually takes to measure the heap. So it's difficult to make the x-axis comparable. Going up the y-axis, we've got the size of the heap dynamically. Well, sorry, it's not the heap, it's the total memory. So here, top is being less precise than our normal measurements. It's, in the case of Z3, you can see it's adding, but there is some fluctuations. There's this interesting bit where it zips from up and back down again. And then the rather odd behavior, which right at the end, when it's working out its answer, the size of the heap goes up quite a lot for a very short time and then drops back down again. For those people who are operating bang on their memory limits, that's intensely irritating because just as you're about to get the answer, you run out of memory and it doesn't produce an answer, it just fails. In terms of the GNU compiler, we see a very rapid increase in memory usage as the source code is read, and then the memory usage is totally flat until we reach the end. And during that process, it's essentially the compiler is generating and optimizing the machine code, at which point it reads from the heap but doesn't add anything. The same sort of behavior on Clang initially, and then I really don't know what's happening there. So Clang is using vastly more memory to compile the same thing. But I suspect the reality is we're again just adding to the heap. And in Redis, we have this curious stepping, which corresponds to different phases in the benchmark. And that's gem5, just to show how gem5 behaves. And again, this very long flat point where gem5 is actually doing its dynamic simulation. So although that looks constant, this is where the heap is actually being hammered. And I suspect that's where we're actually getting our improvement, our optimization. So to conclude, not all search problems are hard. Sometimes they can be quite easy, sometimes it's worth trying to optimize. The GNU-C library's got 37 runtime parameters. In principle, you can use your favorite optimizer. Here, I've just used Magpie and CMAS, but you could potentially use whatever your favorite optimizer is. Here we see gem5 has this large valley which contains something like 400 quadrillion solutions. If you insist on finding the absolute optimum solution, you make your problem 400 quadrillion times worse. If you're happy to say, oh, 10%, that's good, and stop, it's an easy problem. We looked at 4 other non-trivial C++ programs. They similarly have smooth landscapes, but we're not seeing the large improvement. Z3, we got a few percent, but typically a lot less. And just to reiterate, Magpie can tune source code essentially written in any language where there's an AST available. So it's been demonstrated on C, C++, Java, Python, probably some others that Amrit knows. He's nodding. And it can tune parameters, and it can do all of that simultaneously. The chair's not looking, so I'm going to sneak another. Quick, if the next May, we're going to have the deadline for the human competitive competition. So if you want to win your share of $10,000 for results that are human competitive, then all you need to do is email them to Eric Goodman before Friday the 30th. And she's still not looking, so I'm going to sneak a last one, which is a plug for the GP bibliography. If you have any papers on genetic programming and you want people to find them via the bibliography, then the simplest way of doing that is to send me the reference. There are online ways of adding it as well, but the easy way is just say, Bill, add this. Okay, I shut up now.
Thank you so much, Bill. We thank
Thank you.
We have 2 minutes for questions. Questions in the room? Yeah.
Microphone's coming.
Working? Anyone?
Maybe, is it switched on?
That's okay. Yes, so the fitness function, you had heap usage in the fitness function?
I'm sorry, can you repeat, please?
Sorry, did you use heap usage as your fitness function?
Yeah, so the fitness function is, one is the reduction in the peak heap.
Was was that deterministic enough for fitness calculation? Or did you see a variation between your fitness there?
Oh, so I should have stressed this. One of the, so the question was, did we see a lot of variation in measurements of peak heap usage? The short answer is no. These are well-written pieces of code. They are almost exactly deterministic. One thing I didn't mention was for the GNU compiler and the Clang compiler, there is a very obscure switch which says use the same seed. So that was the seed was specified so to make it easy to check that the object files produced by the compiler when it was run a second time were absolutely identical. So the GNU compiler produces an object file of several tens of kbytes, and one hidden part of the fitness function is, did I break the compiler? No, I didn't break the compiler because it's produced exactly the same object file as it did before. By using the seeding of the pseudo-random number, not only does it look the same semantically, but it is binarily identical. And again, the other pieces of software, I've done my best to ensure running them repeatedly, they produce exactly the same answer. And so in terms of a heap, which is, again, something buried within the code, in these examples, it was exactly deterministic. That makes fitness testing so much easier. Thank you.